All right. So we're going to spend the next 90 minutes together talking about SolidWorks simulation. So we might as well get acquainted. I'm going to ask just a couple of questions to have a feeling about the audience that we have here today. I assume that you are a bit familiar with SolidWorks simulation. So my first question would be, how many simulations you have run, like how much experience you have? For instance, which of you has run maybe between 0 and 50 simulations? Raise your hand. All right, a good portion. Maybe between 50 and, let's say, 200, like that would be an average experience. Okay. Anybody with more than like 200 simulations run? Okay, so we have also some experienced users here. Excellent. That's good. And it's good that we have a variety of people in the audience, because I'm going to present concepts and tips and tricks that also cover a broad range of abilities. So it's good to have an audience like yours today. Excellent. So, I'm going to introduce myself now. My name is Julien Boissat. I am a tech support engineer for simulation products. I work out of a home office in France, in Bordeaux. So, yes, Bordeaux, I live in the middle of the vineyards. And I am French, so I like wine, and I eat frog legs and snails at times, cooked. and smelly cheese, thank you, and smelly steak. And of course, all the cliches that you know about French people are true. That goes without saying. And and I've been doing, I've been a support engineer for quite a time now, about 10 years, doing simulations all day long. So yeah, I have quite a bit of experience with that as well. Now, since I have a home office, some of my coworkers go and say that in my house, their simulations are done like pretty much 24 hours a day, and that I do my simulations during daytime, and my wife mostly simulates at night, but I have no idea what they're talking about. All right, let's talk about the agenda. First, we're going to cover some concepts. We're going to talk about the stress concentrations and singularities. We'll move to talking about solver speed and how long it takes for your simulations to run to completion. And then we'll cover some tips and tricks. So first of all, stress concentrations and singularities. I make the distinction between them, and I guess it would be worthwhile to go through some definitions. So stress concentrations and singularities both appear as zones of local higher stress. They stick out, they stand out as zones with higher stress, but there's a difference between them. Stress concentration will happen at a zone where there's no sharp geometrical discontinuity, and typically where there's no concentrated load or fixture. While its stress singularity will happen where you have a sharp discontinuity, just like a sharp reentrant angle, a sharp corner, or where you have a concentrated load and fixture. As a consequence, where you have a stress concentration, the stresses will eventually converge when the mesh is refined. Refining the mesh using smaller and smaller elements will eventually have the local stresses converge to the effective value. Whereas where you have a singularity, the stresses will never converge. They will increase ever and ever every time you refine the mesh locally. And as a consequence, where you have a stress concentration, the converged value can be trusted. That's the predicted value, and it's a fixed value. But for stress singularity, you cannot take whatever value you get, well, at face value. You should not take that into consideration without a lot of thinking. So we're going to go through a little quiz, and I have two models here on the screen. Model A, if you can see, there's a fixture right here, and there's a force, upward force right there, and here is the zone where you have higher stresses. Now, please raise your hand if you think that here you have a stress concentration. Few people, maybe 10% of the crowd, who thinks that there's a stress singularity there? A bit more. All right, yeah, you would have a stress singularity there because of the perfectly sharp reentrant corner. Now, model B, fixture is right there. It's on the, there's a split line. The cylindrical face here is fixed, and then we have an upward force. And a vote on B. Who thinks there is a stress concentration there? A bit more than earlier. Who thinks there's a singularity there? Nobody. Oh, a couple of people, yes. And actually, there is a stress. It's a singularity that you got there. It's not as obvious as for the other one, but that's true. I encourage you, if you don't take my word for it, to model this. It's very simple, and run and refine and refine and refine further the mesh right there, and you'll see that the stress is ever increasing. Two more examples with the shell mesh now. We were using a solid mesh earlier. Model C, you have the four edges of this. We have the four edges of this square hole. They're fixed, and we have a locally high stress there. Who votes for a stress concentration? Nobody. Stress singularity. All right, you get the drill. And finally here for this model, for model D here, where we have this circular edge that is fixed, and we have a local high stress there. Who votes for a stress concentration that will eventually converge? Yes, cool, stress singularity. No, it's not a stress singularity. It is a stress concentration. All right. So now, this is maybe still a bit confusing for you. So we're going to go through an example. All right. Let me drop this for a moment. Cool. Oops. Sorry about that. So we have some kind of cantilever bar here. 10 millimeters thick, 100 millimeters long. We have a sharp reentrant corner there, so that's going to give us a stress singularity. If you do the math to calculate the theoretical stress right there, it's given by this formula, and you would get a 300 MPAs, megapascals, predicted nominal stress. What I'm going to show you in the following slides are the effect of two combined phenomena that we're going to encounter right there and there. First of all is the effect of the stress singularity, which will make the stress value diverge and get higher and higher and higher. And the second one is stress dilution. And the stress dilution will be a local lowering of the stresses at the corner due to averaging at nodes common to elements with very different stresses. I will show you that graphically a bit later. And we're going to see that the relative influence of each of these phenomena depends on the local element size. So let's take a look at the first example. If I can go to the next. All right. Cool. So here we mesh the model with an element size that's half the thickness. We can see the local high stress is there, but you can see that the max is not at the corner. The max is slightly off. And if I was to plot the stresses, so you got the stress value on the vertical axis, and on the horizontal axis, you have the distance to this point along there. Okay? You see that close to the corner, there's a drop. The stresses go down. And that's counterintuitive, isn't it? Oh, come on. So this is what's happening. There are two ways of doing stress averaging and getting results. So you got the elemental results. So you average the stresses within each element. And here you got the nodal averaging. What happens here is that if you take the stress at the corner node, the nodal stress will be the average stress when you take into account the value for this node as the node belongs to the different elements. So here you have the value here will be the average of this value there plus this one, and this one. You take the average of that. So there is a dilution, a local dilution of the stress value, all right, because it's average over only one highly stressed element and three elements with low stress. And this is what you see there. This node here belongs to three elements. Two of them are highly stressed. All right, so the stress is high, but for this one, the corner one, it's only one highly stressed element, three with low stress. So that's where you get that stress dilution. Very painful. All right. If you refine the mesh, now you have 4 elements across the thickness. You see that the stress dilution and the stress singularity roughly cancel out. It's less clear than earlier. The max is still not at the corner. If you refine further, this is what you get. So now we have 8 elements across the thickness. Now you see that the stress singularity starts being dominant. The max stress is at the corner. Refine further. You see the stress singularity that starts peeking out and showing really nicely. Refine further, and I'm not using a uniform mesh anymore because it wouldn't make any sense. And it goes even further. And I have now 870 megapascals. Refine further, now I have 3,300, and it would go on and on and on. But if I plot all these graphs together and just zoom in on this portion, because we know that over there, it's always the same thing, but just focus on this portion between 0 and 20 millimeters away from the corner. This is what we get. So each curve represents the stresses with a different element size. Now you see one thing. First of all, if you use an element size that's 10 millimeter, that's equal to the thickness, then you're just off. But for everything else, pretty much, you get a curve that is superimposed, and that if you continue it in a straight line, disregarding what happens very close to the corner, you end up to 300. That's the nominal stress that we were able to calculate by hand. All right? So even where you have a stress singularity, you cannot trust the value that you get there, but you can continue in a straight line and get the nominal stress. That is the stress that does not take into account the effect of the corner. Now, in real life, perfectly sharp corners don't exist. So let's assume that we have a very small radius there, which was not previously modeled, but that we can now decide to take into account. Now, books will tell us the local stress concentration factor, and it's a multiplier that you need to use with respect to the nominal stress, and then you get the expected stress value there. So I'm using this table from a book called Mechanical Engineering Design, and here the predicted stress concentration factor is about 2.5, which would give us a predicted stress there of 750. And sure enough, when the fillet here is modeled, and we use a relatively small element size, we get to a value that's close to there. And we can try out what happens by using different mesh sizes there and see what effect it has on the stress. And this is what you get. Now, this graph is a bit more complex than the others. The red curve represents the maximum stress that we get on the fillet. The blue curve represents the number of nodes that are created by the mesh on the 90-degree curved edge. So what you see is that if I have two elements on the curved edge, you get bad, and I used an element size of 1 millimeter, you don't get results that are all that good. But as you refine, and I'm using 0.5 millimeter elements, I get better, and then more. And what's nice to see is that it continues in a straight line, so it is very predictable where you are going to end up. I went to a local mesh refinement such that I had 99 nodes, on the 90-degree bend, right? 90-degree curved edge. But if I went to 1,000, this value would not have changed at all. This curve, the blue curve, would have peaked up to the sky, but we would converge. And notice how we converge nicely to 750, give or take, right? So this is showing you that when you have a stress concentration, not only will you eventually converge to the actual stress, but you don't need to refine it all the way to 99 elements. All you need to do is run it once, maybe with 3 or 4 or 5 elements across the 90-degree bend, and then just continuing the curve in a straight line will end up giving you exactly the final stress that you would get with an infinite number of nodes. To summarize all that, what can be said is that when you have a stress singularities, you can never trust the value that you read off the screen. However, sometimes, because you can continue the curve all the way to the 300 MPAs that we got, you get the nominal stress. If you're lucky enough to be in a situation that is taken into account in a textbook, you can get the stress concentration factor, multiply them together, and get the actual stress that you will have. For a stress concentration, however, you should not read take the value you see at face value when you have a coarse or a medium mesh, but only when you have a fine mesh. However, when you have a coarse or medium mesh, the correct stress value can still be derived by extrapolation from several runs, just like I showed that the 750 mark could be derived from doing this line with this value, and that value. You continue in a straight line, and you get it. So we can ask a question a bit further, because 750 MPAs is quite a high value, and you might expect some yielding to happen there. So what if you actually had some local yielding? Well, this is what I've run here, and the fillet is modeled there. And on this graph, I'm presenting the previous linear stress, the stress from the linear study, the static study, and I'm presenting in yellow the stress from the nonlinear analysis, in which the material yields at 300 MPa. So anything that comes from the stress concentration will cause local yielding. What happens is that even though we predicted with the linear study a stress of 750 MPAs, now the stress is barely beyond 300, the yield strength. Not only that, the yield area is quite small, right? We're not yielding across the entire cross-section there. What you can see also is that this yellow curve is above the red curve. If I was to plot the portion of the model with stresses higher than 280 MPAs for the linear static analysis, I'd get this zone. With the nonlinear analysis, where the material yields, you see that I get a much larger zone. Everything happens as if there was a transfer of this area, this high stress zone, a transfer down over there to the area surrounding the yielded zone. And that's called plastic adaptation or elastoplastic stress relaxation. These are the two words, the two expressions that are commonly used for that. The material yielding prevented the stress from skyrocketing at the expense of two increases. The first is the increase, a stress increase all around the yielded zone. This is what I showed in my previous slide. And the other increase is an increase in the deflection. Now, reflecting on this, we can ask three questions about the last model that we saw. First of all, will it break? Second question, is it safe? And third question is it acceptable? Now notice that these questions are different, they're not equivalent. So a structure can not break and still be unsafe. And a structure can be safe from a reasonable standpoint, but still not be acceptable because you have other considerations to take into account. So here, will it break? No. The structure is not predicted to break. It will yield locally, but it is not predicted to break. Not at all. Is it safe? Well, it depends on how the load that we had is applied and how many times. If you apply it dynamically, you will have other effects, like dynamic effects, that you will have to take into account. And if you apply this load many times, 20, 30 more times, you will have fatigue. So fatigue will be a concern. And I'm not talking about the high cycle fatigue. I'm talking about the type of fatigue that you get from when you bend back and forth a little strip of metal, and then after 20 or so bends, then it ends up breaking. And is it acceptable? Well, it will depend on other considerations like the regulatory environment that you have to go with, some specific requirements that you only know about that are specific to the type of design that you're doing, and to your customs. And of course, they're all industry specific. So the answer is always specific to a certain industry, and no general assumption can be, and no firm answer can be given at this point. All right. We're going to move to solver speed, which is a big factor now. The variety of machines that you can have is greater than ever. There are lots of study types that you can run, and the time your analysis will take is a result of numerous factors. The type of machine you have, the number of CPUs that you have, the amount of RAM, the type of study, your study properties, the type of elements you have, whether you take contacts into account or not, whether you have bonded contact with compatible or incompatible mesh, all these will have an effect on the solver speed. And to give you a bit of perspective on what's going on, I'm presenting you with this slide where we see that not everything in SolidWorks and SolidWorks simulation is multi-CPU enabled. The user interface is not multi-core, multi-processor. The standard mesher Not either. The curvature-based measure, however, is. And our solvers, you know, the two solvers that we currently have, the FFE Plus and the sparse solvers, are also partially multi-threaded. But not everything about the solvers is multi-threaded, as we were going to see here. This is the slide for the FFE Plus solver. And solving an analysis involves several steps, and each step can or cannot use multiple cores or CPUs. Forming the surface-to-surface bonding is something that you only need to do when you have incompatible mesh. So you bond a shell to a solid. Wherever you tell the program to bond them, it will create a surface-to-surface bonding. This is only one core. Many other steps are multi-core, but the stress calculation at the end, only one core can be used. When it comes to the sparse solver, you see that you also have stages where only one core can be used. So because some portions of the analysis only use one core versus others use several cores, now you're going to have to find the right balance between, well, ideally having only one core that is extra powerful so that the stages that only use one core are optimized, and having many, many cores so that the stages that are multi-core enabled can benefit from the number of cores that you have. You're going to have to find a balance between that. And I'm presenting you here with a graph that shows the solver performance for the same model as you increase the number of cores that the solver will use. So when you use one core, well, by definition, it's 100%. Of the time is whatever, we call it 100%. And then you run again with two cores, then you get a decrease in the time, and then you add more, more, more. So we go with one core, two cores, 3, 4. Well, there's no, I didn't do it with 5, but then 6, and so on and so forth. What you see is that for the FFE Plus, it really doesn't bring any advantage to have a machine with more than 4 cores, unless you're running this and then you're doing something else at the same time. For the sparse solver, however, you'll notice two things. Number one, it makes sense to keep on increasing all the way maybe to something between 6 or 8 cores, because we take advantage of these cores. You also notice that the time decrease is much sharper. So the sparse solver is a lot more efficient in taking advantage of multiple cores compared to the iterative solver, FFE Plus. And you notice an effect that when you are using the total number of cores, you get an extra boost in solution time. So you might say, well, let's use the sparse solver all the time, if it's so great. Now, but there's a drawback from using the sparse solver. It's the memory requirement. The sparse solver is 10 times more memory demanding than the FFE Plus solver. So in a regular machine, maybe you have 12 gigs of RAM. With the sparse solver, you will be able to run maybe something with 2 million degrees of freedom, but not more, because you'll be saturating your memory. The FFE Plus solver being a lot more efficient, so when you have 10 gigs of RAM, you can go a lot with a lot more, a lot bigger model. This slide shows you the expected improvement in time to solve, whether you're using the sparse solver or the FFE Plus solver, depending on the type of study you're running. And this is a comparison between the solving time with one core versus using 4 cores on a 4-core machine. Now you see that this sparse solver is very efficient at using cores for static and thermal analysis. FFP plus solver does an okay job for these three study types, and for nonlinear you get a slight improvement, not much. And dynamic and thermal analysis, nothing for the FFE plus solver. But this is all relative, right? I'm not directly comparing the solution time for the FFE plus to the sparse solver solution time and comparing each one in its own world. But if you take a look at samples and you run it and you compare all together, what you see is that, for instance, with a simple part solid mesh, one load and restraint, that's the most basic type of model that you can have, you'll see that even though you get a huge increase in performance between 4 and 1 core for the sparse solver, and you get a much smaller decrease in solution time there, it's still the FFE plus that is much, much better for that type of analysis. If we take a second model, this time it's a solid mesh, but it has bolt connectors and node-to-surface contacts with large displacement. So we're adding difficulties. These are typically difficulties for the speed of the FFE plus solver. Bolt connectors, contacts. What you see now is that the worst solution time is with sparse and 1 core, but the best solution time is also with the sparse solver. Because the sparse solver is so good at taking advantage of the multiple cores that it becomes the best one when you have them. And you can do that with different types of models, and you'll see a pattern will emerge of which solver will be the fastest one. And the pattern leads you to have simple rules that you can implement. And I'm summarizing them here. So the recommendation for static analysis, which is, I guess, what you mostly run, is this. Use the direct sparse if you have enough RAM and multiple CPUs, because I doubt you will have computers with only 2 of them now. So it's probably 4, 6, 8, or maybe 12. So use it when you have models with no penetration contacts, especially with friction. When you have models with parts with widely different material properties. I'm talking about steel and rubber together, maybe, or steel and plastic. And when you're solving models where incompatible mesh is bonded using constraint equations. And that will happen where you're using mixed mesh. So beams and solids, shells and solids, shells and beams, right? Different element types. Or where you are using bonded contact sets. And I'm making a distinction between the global bonded contact that you can define that applies in your entire model and what you define manually. All of the cases FFE plus. For nonlinear analysis, I have a simpler rule, and you're going to like that. Always use the sparse. Yes, sorry.
How much RAM is enough? When you say RAM, 32?
All right. You have for any machine now, you need about 2 gigs for the operating system and everything that's around Outlook, whatever it is that you have open internet browser. All right. So you take whatever amount of RAM you have, you remove 2 gigs. That's what's left. All right. With what's left, you take 500 megabytes for SolidWorks itself, something like that. And then what's left is available for your analysis. And this is the amount of RAM that you have available for analysis on your machine. And then I said that it was for 1 gigabyte of available RAM, you can have 200,000 degrees of freedom with the sparse solver. So that gives you the maximum size of the analysis you can run. Don't try to use your swap space, you know, your hard disk drive, to complement your RAM. Okay? It's possible only marginally, like when you're missing maybe 10%. You need 10 extra percent of RAM, maybe it's going to work, right? But if you're trying to double your RAM by having a huge swap space, forget about it. Did I answer your question?
Yep.
Excellent. What I'm presenting, what I'm saying now, I put also in the SolidWorks knowledge base on the customer portal. These are the solution IDs that you may type in the search tool. And you'll get some of the graphs that I presented, some of the tables that I presented, and then some text that explains what I did. I know sometimes data can be not very easy to find. You know, you get so much hits, so many hits when you search for stuff. So if you enter that, you'll get to them directly. And by the way, this presentation will be available with the proceedings of the conference. So you'll get the PowerPoint, and you'll get also some of the models that I will be presenting shortly. Cool. All right, tips and tricks. We're going to talk briefly about dealing with time-dependent results that you will encounter when you're running transient thermal analysis or nonlinear analysis, for instance, or dynamic analysis also is another good example. So for that type, for taking a look at these results, these time dependence results, there's a very, very nice plot called envelope plot. And this plot will give you in a single result the node's max or min value, depending on what you choose, throughout all the time steps that have been calculated. So for at node number 1, it may take the result from time step 2, and then at node number 2, it will take the results from time step 5, and so on and so forth. This is very, very efficient to get your results. So if we have an example here of a nonlinear study when one force here peaks and goes back down at one end, and then afterward you get another force on the other side that starts and goes back, you're not going to get the max stress at different locations at the same time. And that's when an envelope plot will come very handy, because what you're going to have is first you're going to get only half of the model stressed, and then the other one, but not at the same time. So you'd have to juggle between different plots. With the envelope plot, when you define a stress plot, you choose this option, which plots bounds across all steps. You use the maximum, and you got this summary of everything. So if I was to have this analysis, this is the regular stress plot that you would get. And right here you have the envelope plot where this option was chosen and we choose the maximum across all steps. What is nice about that is that you can do a probing the value, get the graph, and from the max, you can see very easily when it took place. Now, sensors now have the capability of taking advantage of the transient results. So once you create a transient sensor for stress, you automatically get this plot which shows you what value the maximum stress takes at every single time step in your simulation. This is the transient sensors are a new feature of version 2013, and you choose simulation data then the type of quantity you want, and then the type here is transient. And that's how you get the plot that I just showed you. Another quick example. For thermal analysis, you have 4 chips, 4 heat powers, and each with its own time curve. And you can easily find the maximum temperature in the entire model. Here I have my model, and each chip has a heat power with its own time curve. It's different for each one of them. So what you do is you create a thermal plot for temperature, Celsius maybe, and then you use the plot bound across all steps. Then you got that, and you can, by the way, do you know this? You can double click here, and it opens the property manager to show the max annotation. Nice thing. If you want to change the unit, you just double click here. All right, let me hide this. Go back here. All right. And you can double click and change the units maybe to Fahrenheit if you want. There's another customization that you can do. Right click and go to customize, you go to your commands, simulation, and then this one here that you can drag is the plot settings, and it allows you with one click to access there and be able to plot the mesh if you want. So you don't have to go here and then wonder which one it is and use the menu there. And once again, the sensor, same sensor that I created earlier, will give you when the maximum temperature takes place, and the location, you got it there. I'll show you a bit later that these graphs that you can also get for nonlinear analysis and when you have reaction force or contact. And it's a new thing that happened, that was introduced in version 2012 SP2. All right, let's move on to this interesting model. And it's an interesting model because it's an interesting model. And it's an interesting model. And it's so interesting. And you find that funny? Come on, have pity for the Frenchman. All right, let's go. Okay, let's investigate.
I'm glad we're not alone.
All right, there you go. All right, let's investigate. I opened the model, and SolidWorks froze, right? Let me open SolidWorks again and try a little something. In the add-ins, I will remove SolidWorks simulation for the moment. And I'll take the same model and open it. All right, it's not frozen. Tools, add-ins, simulation. All right, it's not moving at all. All right.
See, we're not alone.
But how about we try to be smart? Simulation cleaning utility. I have it here, but I could also get it from the installation of SolidWorks simulation. Let me Control C, Control V, browse, filter to assemblies, open this assembly, which that's the one I just opened. And I want to clean the file of all data from simulation. Clean file. All right. Cool. Close. SolidWorks. Simulation is added in, and it's not frozen no more. How is that cool?
That is too cool.
All right, presenting the simulation cleaning utility for cases like this. The simulation cleaning utility fixes corrupted files. It allows you, even though your file may not be corrupted, but it allows you to get a fresh start. Maybe it's a file you have been working with for a long time. You created so many simulations you can't remember anymore. You created studies, deleted them, recreated, copied, pasted, everything. Your file got so large, it takes time to open now. This tool will let you get back to a fresh start. And it is installed with every single SolidWorks simulation installation, typically in C program files, SolidWorks Corp, SolidWorks simulation, and then utilities. All available to you guys, and it works for everything: motion simulation, sustainability, flow simulation and flow express, and everything. So yeah, SolidWorks crash on my command only.
Okay, so we're no longer.
All right. Okay, hydrostatic pressure is something that a lot of people have trouble with. And, oh yeah, take a look. That's a model of a swimming pool, just simple thing. And mesh with surface bodies and weldments, and so it's a mixed mesh. And you don't have to worry about bonded contact anymore, because in 2012 now, global bonded contact can also apply to a lot of places. And here, the imprint is automatic. And we will follow the guidelines from solution that I created, and the number here is here again. And the guideline makes it as simple as possible to apply a non-uniform hydrostatic pressure that varies with the depth. And it goes like this. First of all, you create an appropriate coordinate system. The coordinate system has to be at the top of the water or liquid with the y direction going downward. So at the top, y goes downward. You apply a normal pressure because the pressure will be normal on the faces. And there you activate the non-uniform distribution, and you have to enter some values. In the pressure value field, that's right there with the first circle, you enter the fluid's mass density multiplied by gravity. And that's the value. And I recommend using the SI system for ease and not try to use megapascals there. That's like SI, pure SI, and everything will go smoothly. Once you've done that, you multiply the mass density with the gravity, then you enter a value of 1 here, and 0 everything else. And your coordinate system is selected there. And that's all you need to do. So that's what's been done here, as you can see. And I will give you this model, by the way. So there we go. You see my coordinate system right there. All the faces have been selected. Everything is cool. I can show the mesh right there. You see the imprint that has been done automatically. You can see the outline of the weldment there. Now, if your structure is deep underwater and it's inconvenient to place the origin of the coordinate system at the top level of the water or whatever liquid you have, you can put it at a certain depth. If you choose to do so, then you follow the same rules as before, but you enter the depth of the coordinate system's origin in meters as the constant value right there. So if the coordinate system's origin is 100 meters below the surface, you enter 100, not minus 100. And that's all you have to do. So let's take a look at the study results that we got for this analysis. I can plot the displacements, for instance. Now, you see how each panel kind of like ballooned? That may not feel right. And that's because flat panels, when they have pressure, they have a stiffness that varies and doesn't stay the same. When something is perfectly flat and you press on it, you start pressing, you only get a bending stiffness. But as it deforms, you start to have tension throughout the thickness, and this increases the stiffness of the plate. This is an effect that is called stress stiffening, or it's called in-plane effect in the interface. And I can show you, we have an option to take that into account. It's right there, use in-plane effect. And I did not use it there. And this in-plane effect is an approximate way of taking this type of stress stiffening effect into account. It's not perfect, but it does a job. And if I run exactly the same analysis with in-plane effect, you'll see that the value here you got for the maximum deflection is much lower than before. Right? It decreased. But the best results you'll get with a nonlinear analysis. Because with a nonlinear analysis, you can control a bit better how often the stiffness of the model will be recalculated. You know, for nonlinear analysis, we apply the loads gradually, incrementally, and you can recalculate the stiffness matrix with every step, and that's how you capture best the evolution of the stiffness of the model when loaded. You can go to this solution that I'm presenting here that explains exactly how the in-plane effect option works, how it improves the capture of this stress stiffening effect, what the limitations are, and showing also that the best results are always obtained with a nonlinear large displacement analysis. Many times, when you have a model with weldments and shells created from surfaces and solids, and you wonder where the center of gravity of your model is located, and what the total mass is. And it may be different from the SolidWorks, what SolidWorks will give you, because SolidWorks doesn't know the thickness and material for the surface bodies that you created. It doesn't know whether you created additional mass, like a remote mass or distributed mass on your model. And you may have changed the materials, right? You can define the materials in your study. In these cases, to get the actual center of gravity location, and the total mass plus other properties, you should create a static study, define gravity, run the simulation. Then, in the output file, it's a very interesting file that's created by the solver. It's located with all the other result files. The output file can be opened with any text editor, and it will contain information about the properties of your study, some results for reaction forces, for stresses, for max deflection, for the strain energy in the model. But also it contains a table where you will read the mass, the volume, the weight, taking into account the gravity, and then some other properties like center of gravity, but you'll have the mass moments of inertia and a lot of useful information. If you need to find where your CG is from everything you set up in your study, that's where you'll find it. A very nice tool that I want to show you is the search tool. The search tool is actually this little thing that you get here at the top of the simulation manager. Do you guys, who knows that it exists? It's barely noticeable. Okay, a number, who uses it for simulation? All right, this number will increase. All right, let me close this. All right, this is just a model that I created to show you why you might want to use it. And it's a model, it's a pattern of the same part. And this part has two surface bodies and then one extrusion and structural member. And it has been patterned many times. So there's like, I can't even scroll and show you the whole tree. There's so much if I expand everything. But what I want to show you is that if I mesh it, it's going to tell me that it can, because thickness is not defined for one or more shells. So typically what you would do here is say, oh man, all right, which one is it? And you go there and do stuff, but then what is the problem here? The problem is that thickness is not defined. Not, oh, I don't even have to type defined. Look, it found it. Because in my surface body, it says here thickness not defined. So I can isolate very easily the items in my tree based on simple keywords, such as thickness not defined. You can use it for other things, for instance. So let me clear that so that I have the whole tree once again. All the bodies here are alloy steel, but I know that I created one out of iron. And I could ask, okay, go and find it. It's like finding a needle in a haystack. But same thing, if you type iron, there you go. That's the one over there. I can see it. It's this one. The search tool is very powerful when you have complex models. When you created many contacts, when you created many forces, many loads, when you have a tree structure that is long, you can use it to isolate the types of bodies that you want. For instance, I want to isolate all the oops, American keyboard, I mean. See, I can isolate all the surface bodies here quite easily. It's a tool that's very convenient when you have complex models. Very simple models, frankly, you don't really need it, but complex models, that comes in super handy. All right. Cool. Awesome. I have about 25 minutes, and it's awesome because we're right on time. I'm going to have some time to go into the details of these models. There's something that is always a bit difficult for users. It's how to handle analysis when you have interference between your component in their modeled state. And there are several ways to go about that. And I'm going to explain to you what are the ways. These models that I'm going to be showing here, they will be part of the proceedings. So you'll get the models with the studies, everything set. The explanation will be, well, is recorded right now. And, well, you'll have everything. Cool. So this is a model where we have a little star. It looks like a gear and another part here that goes between the teeth. And with this first example, I'm going to show you the solution with non-zero initial displacement. All right. So this is my model, and as you can see as I zoom in, we have initial interference between the parts. The purpose of this simulation is to hold these two circles in place and to have the little star rotate about its center. So one way to do that, frankly, would be to create a different configuration. I could create a different configuration. Let me zoom in so that you see the different configuration. When I activate this configuration, see? I cleared out the interference. And what I did actually is for this configuration, I modified the distance here. I modified the distance. And I created a new configuration where my part is just a bit higher. So all I have to do now, if I want to run that, is to, move it back to its original place. So that's 0.1 millimeter down. So that's what I would do here. See, I put it back down 1 millimeter. And this is the stress curve that I use. So from 0 to 0.1 second, I move it back down. And then I leave it constant. And then the other prescribed displacement will be the rotation of my little star. And it will take place from time 0.1 all the way till the end. If I do that, let me take a look at the displacements. I'm using time step of 1 and reducing speed to the minimum. And hopefully you see that it moves down and then it rotates. All right. First solution, create a new configuration wherever possible to clear out your initial interference. Then move the parts back into place and then do the simulation that you want. But that's nice, but maybe that's inconvenient for you to create a separate configuration. So we can go back to the default configuration and define a non-zero initial displacement. And what I mean by that is that I can create a curve where the value is not equal to 0 when time equals 0. So at time equals 0, that's the initial condition that will be taken into account by the solver. My part will not be where it is, but it will be in a moved position. That's my initial state. And then I release that displacement back to 0, initial location. And then I'll do the rotation of the other part. Second possibility to handle this. And once again, let me add the animate. Commands, simulation, animate here, okay. And once again here, you'll see it move back into place before it rotates. So second possibility, non-zero initial displacement. That's something that may not come naturally to you, but it's perfectly allowed. All right. Cool. I'm going to show you another possibility. Solution with thermal shrinkage. Now here we have a model with a rubber part, it's green here, and we have a metallic ring, and the goal is to put the ring inside the rubber. Now there's no way you can move one with respect to the other to get it inside. It's just not possible. The ring is big, and the rubber part is too small. So what we're going to do is we're going to use thermal shrinkage. And this is how it goes. It's a two-step process. And I'm using 2D analysis here again. The first process is to find out how much you need to lower the temperature of on one of the parts to make it shrink so that you get it where you want. Of course, if you don't want to shrink one, you can, well, if you don't want to cool one part to make it shrink, you can heat up the other one to make it expand. It's about equivalent and it's your choice, but it's the same method. So here I defined a zero temperature, which is my temperature without it's my reference temperature at zero strain. So I don't want to change the temperature of the rubber part, but I want to change the temperature of this steel ring. And I'm lowering it down to minus 150 Celsius. And I'm using a special steel. Maybe I'll go back to this. It's orthotropic so that it only shrinks in the direction that I want. And I used a slightly higher thermal expansion coefficient. But the point is that when I run the analysis, I'm able to make it shrink so that it shrinks so much that it goes on the right and on the correct side of the rubber part. See that? It shrinks and it moves down. You can, I guess I could do that. Let me define a displacement plot, show us 3D, maybe with 270. So this is what happened, right? Now it's inside. You can see it clearly now that the ring is inside? Cool. So I need to find out what is the right temperature to get it where I want. And I see that at time, with my step number 12, the temperature is 0.95 times 150. That's about 140 Celsius. It's right where I want. So then what I do is I define another study. I just duplicated the study. And I put my part at minus 140 degrees Celsius initially. Time step equals 0. It's cool. It's already very cold and it's shrunk. And then I release it gradually to 0 so that it comes back to its original size. And when I do that, this is the time plot step 2 that I got, but I can animate it. Animate. Let me make it a bit finer. And this is what you get. It starts on the right, on the correct side, and then you release it so that it gets back into to its original size. Of course, you probably wouldn't do that in reality to mount them together, right? You probably use a tool to expand one versus the other. But whatever method you use, at the end, you'll get in a shape and a displacement and a stress state that is exactly the same as what we have here. Thermal shrinkage. is the second option that you can use to do that. Now, another example here that would be interesting to run is this, where you have a seal, and the seal, of course, the rubber seal, penetrates, has to deform to get in the groove that it's supposed to be in, and that's something that I could show you, but not, because there's an option here that you will need, which is to update the load direction with the deflection to ensure that the pressure, because there's a seal, it's because there's a fluid and there's pressure, and you need the pressure direction to be always perpendicular to the surface of the model, whatever its deformed shape is, right? That's an option that we have, or well, we had in 2D until version 2011 in SP3, and you don't have it anymore. It's grayed out, so you can't run this type of analysis anymore. Too bad. But if I was a user and I wanted to use the update load direction, I try to notify SolidWorks that I know what's going on. So this is what I would do. I'd log in the customer portal. I would go to the knowledge base. I would type update load direction, and I would search. I'd filter to only take a look at SPRs to see if there's any known thing about that. And I would find the SPR like this, This one asks to revert this SPR and make upload direction with deflection available again in 2D, blah, blah, blah. Right? That sounds like something that I would want, right? And then on the left-hand side, I noticed that there's this. Find what you were looking for? Yes, but notify me when this is fixed. And this is the way that you can let us know which SPRs you are interested in having fixed or having monitored. And you will receive emails when if you do this on your account, you'll receive an email notification when it has been fixed. Now, luckily, the option will be back in 2013 SP0, SP2, which is due next week, something like that. I have the EV. The evaluation version is already out, but this will be possible very, very, very soon. Now, at SolidWorks World, we have only SP1 installed, so I cannot show you this, but I'll show you something roughly equivalent. And it's a shaft with bellows, right? That's what you call it, right? And you see the initial interference there, right? And the purpose of this simulation is to, maintain the end face, the annular face there fixed, and then to pull the shaft so that you compress the bellows. And I thought that'd be something interesting to show you. Because with this example, we're doing, okay, I'm showing you the model. All right, this is section view, so you can see the interference. Cool. And so this is the initial, the displacement that we defined to make the shaft move to the left, and we are defining fixed conditions there. And what I want you to notice here is the shrink fit contact that I defined. This is my solution here. I consider that the interference is not so great that a shrink fit will fail. The interference is mild, and I think it will work. Every time you define a shrink fit in a nonlinear analysis, it gets solved at time step 1. So it's a single step operation for the solver. It works or fails at the first step but you don't get 2 steps, you don't get any intermediate position to solve. And my contact definition here is shrink fit, but I want you to notice that I'm not just selecting the faces, that the edges that are in the penetration zone. I'm also selecting whatever makes sense from a logical, physical standpoint. I'm selecting a bunch of edges from this bellows, and I'm selecting those 3 purple edges that you see here from my shaft. It's a common mistake that we see to try to use only, well, here would be 1 edge in the first box and 1 edge in the second box, and then you end up with things with a list of contact sets that's longer than my arm, and it's very, very difficult to manage. Here, there's shrink fit, there's initial penetration, so I select that, but I extend that to something that makes sense. I group them from a physical, logical standpoint. Now, I'm going to show you the stresses at time step 1 to show you that at time step 1 we got the initial interference resolved correctly and everything looks fine. And let's animate. Move this a bit to the side. Cool. What's going to happen? Check this out. Bang, bang. How cool is that? Is that nice? Not only that, but you can also create it, of course, with the 3D view. Check this out. How nice that looks. Wouldn't that look good in a report? Yeah. I think so, right? And of course, you can animate it. Now, with 3D, it will take a little bit of time to animate all 53 steps, but the result is quite nice. Couple of questions while it creates the animation? No? All right, we can just watch and...
I have a question.
Oh, you do have? Yes.
How does the solver pick which bellows it collapses on?
All right. The question is how does the solver choose which bellows it will collapse on? And the answer is that it is basically random, just like it would be in reality. In other words, as soon as one starts to buckle, then it reduces the stiffness locally, and it will buckle further until it reestablishes contact with the other bellows right next to it. So how, in reality, it will be a manufacturing defect that will make one slightly weaker than the other, and then that one will buckle first. For the solver, it will be slight differences in the mesh and where the nodes are exactly located that will slightly change 1 decimal somewhere in the stiffness, and that one will end up buckling first.
So if you used a variable thickness material, you could basically cause it to collapse in a certain way.
Yes. Yes, if you pick your thickness and material, you can make it collapse wherever you want. Yeah? Mm-hmm. How cool is that? I like this. I love this. And you'll have it. You can play with it too later on. Cool. All right. So the nice resources that you can check out for all your information needs are listed there. You probably know that already. I don't need to spend some time on this. I just want to take, well, we have 5 minutes left, I think. I just want to take this opportunity to have a little chat about the SolidWorks World Top 10 list. Who knows, or actually, who doesn't know what the Top 10 list is? All right. The Top 10 list is some kind of global survey that we conduct to provide users with an easy way to tell us how you use the software and how we can improve it to meet your needs. It's a global survey that we conduct, and ideas are, there's one step where people give ideas, and then a second step where people vote, and then we got it all ranked, and then the top 10 ideas are presented live on stage, and I think it's on Wednesday morning, right? And they're presented on stage, and you got 4,500 people cheering for the ideas that they like. That is something. So these are the statistics for this year. We have a total of 424 ideas that were presented by you at large. Most of them were for SolidWorks CAD, and then I'm showing that some were for data management, 27, and then 45 ideas were presented for simulation. 45 ideas. And this is the complete list of the contributors to the ideas. We have 2 employees. That's me. And that's Marlon Benta. He's a product definition guy. It's like he's choosing what he wants to work on, pretty much. Then we have 2 VARs. Alessandro, wow, big contributor. And Alan from Javelin Tech is an American reseller. And only 2 customers, this French customer and this Japanese customer. 6 guys, 2 customers, 2 VARs, 2 employees. And one of them trusted the whole bunch. All right, this is the final score of all 45 simulation ideas. The final score is, you can vote for or against an idea. All right, so you can give an up or a down. And this is the number of hits, the positive votes, the score that it got. Top 14. 14. 14, well, maybe it was 30 votes, and you got like 22 positive and 8 negative, something like that, and you go back to 14. This is the 11th idea, so it doesn't make the top 10 list for simulation. Now, if you want to move it first, you need 3 votes. Okay. Think about this. Think about this. What it takes to make a change. Think about it. This is the final score for all ideas. In red, the ideas for simulation. The top 10 is here. And this is the 10th idea. This one will make the top 10. On stage, on Wednesday morning, in front of Bernard Charles, Bertrand Sicot. The simulation ideas are there. 14 points. You need 7 votes. The first row here can make it on the top 10 list on stage on Wednesday. This is the power you have.
You're putting it on us.
I'm showing you the opportunities. Mark your calendars is my suggestion. This year, November 11th, you pay tribute to your veterans, and you search the SolidWorks forum for the SolidWorks World 2014 Top 10 List idea submission. And you submit ideas. On December 9th, and I'm making up exactly these ideas, but it's going to be in the ballpark, right? This is early in the process. You have 1 month to submit ideas, and then 1 month to vote. And this year we closed on January 4th. December 9th, start voting. Make a difference. I mean, come on. Think of how it would feel and what it would mean if an idea that you submitted made it to the top 10 list. How you would feel personally, but what it would mean also for your company, for your day-to-day job, for how you work with the software. This is an incredible thing to have the idea that you want, something that will make a difference for you, to have shown on stage in the main conference room and have people cheer for it. Come on. Like, and you can make a real difference because the numbers are not that high. One vote really counts. Thank you very much.